The terms strong and strength get used in a number of different ways when we're talking about acids and bases. It's important for us to know what we're really talking about when we use those terms and whether we're talking about something being a strong acid or whether we're talking about a solution being strongly acidic. Strong acids, you can usually find a list of strong acids. There's one in your textbook. And the list of strong acids is typically HCl, HBr, HI, nitric, sulfuric, the first proton of sulfuric, perchloric, and chloric in many cases. So these are acids that we call strong, but what do we mean when we say strong acid? We mean that the acid completely donates all of its H+, right? That's what acids do. So a strong acid donates most of its H+, or all of its H+, or dissociates, breaks apart into H+ and the counterion. But there's a little bit more subtle difference to it than that. When we're talking about a strong acid, what we're really talking about is this equilibrium. So this is a generic equilibrium with an acid interacting with water to give us H3O+ and A-, the conjugate base of that acid. If we look at Ka, if we look at the equilibrium constant expression for this, when we say that an acid is strong, what we're really saying is that the Ka for that acid is product favored, right? And that makes sense, right? Because product favored means that most of it has donated its H+, which is what acids do. So strong acids are those with product favored Kas greater than 1. Weak acids are acids with reactant favored Ka less than 1. We could say the exact same thing about strong bases. So instead of a Ka, now we're going to look at a Kb. So we've got this equation, the base interacting with water to form hydroxide ion and the conjugate acid of that base. Kb is put together similarly, and again, a strong base is one that has a product favored Kb. A weak base is one that has a reactant favored Kb. Now, we have to be a little careful about bases because for hydroxide bases, and a lot of these are hydroxide bases, when we say that something's strong, what we really usually end up meaning is that it's soluble. So from our solubility rules, remember that most hydroxides are insoluble except for group 1 ammonium and a little bit of group 2. So most hydroxide type bases, metal hydroxide type bases especially, are actually weak bases because they're not very soluble. So strong bases have a product favored Kb, but also keep in mind that they have to be soluble in order to get that hydroxide ion into solution. That gets us to the whole idea of water. Is water strong or is water weak? Well, water can react as both an acid or a base. We looked at that previously when we were looking at conjugates, and we can look at our equilibrium expression and the Kw, the ion product of water, the autoionization constant for water, to give us some idea of that. In pure water, right, if all we have is water, the H3O+ concentration has to equal the hydroxide ion concentration, because for every one of these I make one of these. So these two concentrations in pure water have to be identical. At 25 degrees Celsius, Kw, the value of Kw is 10 to the minus 14th. So if those two are equal, then they must each equal 10 to the minus 7th. So now, if we've got a neutral solution at 25 degrees C is one in which the H3O+ concentration is equal to 10 to the minus 7th molar. If we're more acidic than that, if we're in an acidic solution, that acidic solution will have more H3O+. This is the acid of the pair, right? So if H3O plus concentration is greater than 10 to the minus 7th, then we would call that an acidic solution. If it's less than 10 to the minus 7th, we would call that a basic solution. Using all of those numbers can be a little ponderous. So historically, there's been this description of the amount of hydrogen, the amount of H plus, as either the power of hydrogen or the potential of hydrogen, depending exactly how you translate the words around, but this was abbreviated as pH. So whether it's power or potential is pH. And the pH is equal to the negative log of the H plus concentration or the negative log of the H3O plus concentration. These are completely interchangeable. They mean exactly the same thing when we're in aqueous solution. So converting those numbers that we saw on the last slide, a neutral solution has H plus and OH minus equal. pH is 7. The negative log of 10 to the minus 7th is 7. If it's acidic, the pH is less than 7. If it's basic, the pH is more than 7, is greater than 7. Now we have to be a little careful here, especially for anybody who might be looking into a career in healthcare, because we often key in on this idea of pH 7 is neutral, but pH 7 is neutral at 25 degrees Celsius. Equilibrium constant values vary with temperature. So if we're at 25 degrees Celsius, neutral is pH of 7. And just to make it easy on ourselves, unless you have a reason to think the temperature is not 25 degrees Celsius, always think it's 25 degrees Celsius, because then pH, neutral pH is 7. But in biological systems especially, biological temperature, physiological temperature is not 25 degrees Celsius. If your temperature was 25 degrees Celsius, you'd be dead. So we have to keep that in mind, and just looking at the temperature dependence of neutral. Neutral pH is where, or neutral is where H3O plus concentration is equal to OH minus concentration. And the pH of that shifts depending on the temperature. So here is standard conditions, right? Standard temperature has a pH of 7 at neutral, but as we increase temperature, that neutral pH actually decreases, so that by the time we get to body temperature of around 36, 37 degrees Celsius, neutral is actually at about pH 6.8. So keep that in mind if you're working in any condition that's not, just a nice simple little textbook test tube kind of experiment where you've got a pH that's neutral at 7. Okay, let's just do a quick calculation here. This is fairly straightforward, but depending how much you've used logarithms, this can be a little bit of a reminder. So a solution at 25 degrees C, notice I said 25 degrees C so that I could use that neutral is 7, is found to have H3O plus concentration of 3.814 times 10 to the minus 5th molar. What's the pH of this solution, and is it acidic, neutral, or basic? So pH is equal to negative log of the H3O plus concentration. Plugging my value in from the problem, I get that this is at pH 4.4186, and that's less than 7, so this solution is acidic. What if we go the other direction on that calculation? A solution at pH 25, or a solution at 25 degrees C, again, is found to have a pH of 9.1834. What is the H3O plus concentration of this solution, and is it acidic, neutral, or basic? Well, in this case, we can answer the second part first, right? Because if we're at 25 degrees C and the pH is 9, that's definitely a basic solution. But getting getting our answer out, getting our concentration out of there. Concentration of H3O plus is equal to 10 to the negative pH. So plugging that in, we get 6.555 times 10 to the minus 10th molar. That's just a couple quick examples of converting into and out of pH. We're going to have lots of opportunities to do that. Once you know how to plug it in, once you know how to set it up, it's a pretty straightforward little calculation. So get some practice on that, and I will see you next time.